So this is, we're going to go to 2. This is 12.1 to 12.6 worksheet that we were doing on Friday before break for anyone who wasn't there. So for this, it says Nick's new phone is prompting him to choose a 4-digit code. On the screen, it says choose any digit 1 through 7. After typing the first digit, the flashing dash prompts him for a second. As he thinks about his second choice, he wonders how many different passcodes are possible. I need a decision chart. He writes the following diagram on his paper: first digit, second digit, third digit, fourth digit. How many choices are there for each decision? How many different 4-digit passcodes are possible? So I'm going to use his decision chart. So we're using the digits 1 through 7. Okay. So he has 7 choices for his first one, times 7 choices for his second one, times 7 choices for his third one, times 7 choices for his fourth one. So that's going to be 7 to the 4th. And I've got a calculator here on the side. 7 to the 4th is 2,401 different passcodes. What is the probability that Nick's randomly selected 4-digit passcode will be 2763? So there are 2,401 distinct passcodes. This one here is one out of those. So this is going to be 1 over 2,401. That is the probability. Now, on 12-2, how many different 4-digit numbers, passcodes, could he make using the digits 1 through 7? So again, we're doing 4-digit numbers using the digits 1 through 7 if he, and this is a key here, could not use any digit more than once. So that means there's no repetition. So I am going to make a decision chart, okay? And I'm going to have first, second, third, fourth, okay? First, second, third, fourth. And we have the digits 1 through 7 again, but we cannot repeat. So what does that mean? We have 7 choices for the first one, times. Now that 1 is used, I only have 6 left. Now that 2 are used, out of the 7, I only have 5 left. And after 3 are used, out of the 7, I only have 4 left. So we're going to work this out. So I'm going to go 7 times 6 times 5 times 4, and we get 840 different outcomes, different passcodes. Now, what I'm doing when I'm taking 7 times 6 times 5 times 4, or in the problem above, 7 times 7 times 7 times 7, we call that the fundamental counting principle, which is where you take all the ways that the first event can happen, times all the ways the second and the third and the fourth, and so on. That again is called the fundamental counting principle. Okay. Use a decision chart to answer each question below. A game contains 9 discs, each one with the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9 on it. How many different 3-digit numbers can be formed using any 3 discs? Okay, I'm going to just draw this out for you to see what they are talking about. So I just drew 9 little discs. Each disc has the number 1 through 9 on it. And we're going to be picking 3 of these to get our number. So when we're doing this, we're going to have, we're doing, again, 3-digit numbers. So we've got our first, our second, and our third. So for the first one, we have 9 of these to pick from. But once I pick one of them, that one is gone, and now I only have 8 left. And then when I pick that second one, now I only have 7 left. So I I'm not really repeating in this because each time I'm literally taking one of these. So for example, let's say I pick this one, the first one, this one, and then this one. Okay, each time I had 9 for the first, then 8, then 7 choices left. Okay. So when I work this out, 9 times 8 times 7, I end up with 504 different choices. Now on 12-3, what's happening in this one is it says a new lotto game called Quick Spin has 3 wheels, each with numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, equally spaced around the rim. Each wheel is spun once, and the numbers the arrows point to are recorded in order. How many different 3-digit numbers are possible? Let me draw a picture of what this is dealing with. So for this one, I'm going to actually use the spinner where you got 3 separate spinners. Each of them has the numbers 1 through 9. So I've got 1 through 9 on this one, 1 through 9 on this one, 1 through 9 on this one. And so when we spin, each time we have 9 choices on the first one, 9 choices still on the second one, and 9 choices on the third one. So this is different than the one that we were having 9 separate discs. Okay, so in this case, when we are doing the first, the second, and the third, what's going to be happening again is when I spin, every time I am going to be having 9 choices for the first one, 9 choices for the second one, 9 choices for the third one. I can end up getting repeats. That is a possibility. In this case, I haven't gotten any repeats. Okay. Up there, I got repeats. So you see, I got a 1 and a 1 again. So I can have repeats here. So this is really going to be 9 to the third. And when I work out 9 to the third, 9 to the third is 729 different outcomes. Explain the similarities and the differences between part A and part B. The similarities, let's get a text box here, for this is that when we're doing this, a little bigger, and let me just fill, that the similarities are both are 3-digit codes with the numbers 1 through 9. However, I'll say part A with the discs does not allow repetition. While part B with the 3 spinners does allow repetition. Okay, next problem. So on this one, Marcus is selecting classes for next year. He plans to take English, physics, government, pre-calculus, Spanish, and journalism. His school has a 6-period day, so he will have one of these classes each period. How many different schedules are possible and why? So basically for this, we're going to have first period, second period, third period, fourth period, fifth period, and sixth period. And I'm just going to copy this so I've got this so I don't have to type this again. Okay. And I'm going to paste it here. And then I am going to paste one down here to help me with this one. Okay. So in this situation, how many different schedules are possible? So when we're doing this, there's 6 classes for period 1. Okay. Now, after we get that first class chosen, you're not going to repeat that class. You're not going to have that class twice. So then there's only going to be 5, and then 4, and then 3, and then 2, and then 1. So we're going to go 6 times 5 times 4 times 3 times 2 times 1. Really don't need to do it times the 1 because that's not going to change it. 720. So 720 different schedules. Now on the next one, it says how many schedules are possible if pre-calculus is first period. So if we want pre-calculus first period, there's only one way for that to happen. Okay, pre-calculus is going to be that class. Now, one class out of the 6 is chosen, pre-calc. I now have left 5, and then 4, and then 3, and then 2, and then 1. So really, I'm going to be doing 5 times 4 times 3 times 2 times 1, but again, I don't need that 1. So 5 times 4 times 3 times 2, again, times 1 is not going to change anything. I get 120 different classes, different schedules, sorry. What's the probability that Marcus will get pre-calc period 1? So there's 120 ways for that to happen out of 720 different courses. So there's 120 ways for a pre-calc to be period 1. There's 720 different schedules total without any restrictions on what's what period. So when I do this, 120 divided by 720, I get 1.6 repeating, or sorry, 0.16 repeating. So this is going to be 1/6 or 0.16 repeating. So about, in terms of percents, 16.67% chance of it happening. So you can do it as a fraction, you can do it as a decimal, you can do it as a percent. Fraction's fine, you can leave it as a fraction. Now, what is the probability that Marcus will get both first period pre-calc and second period physics? So for this one, first period pre-calc, one way for that to happen. Second period physics, one way for that to happen. Now that we've done that, we have 2 classes out of 6 gone. So now I'm going to have 4, and then 3, and then 2, and then 1. So I am basically going to do 4 times 3 times 2, which is 24 different schedules. Now, they're asking us for probability. So the probability is going to be 24 out of the 720 schedules. Let's move this slightly. And so 24 divided by 720 is, as a fraction, 1/30th. As a decimal, 0.03 repeating, 0.03 repeating, or 3.3 repeating percent. Okay, so now the next one is asking us to do the following. On your calculator, find a function labeled n factorial is how we read it, with exclamation point. It's called factorial. On many graphing calculators, it's in the math menu and probability submenu. Now, if you're doing it on Desmos, and I'm just using a scientific Desmos, okay, which is, you can get to on Desmos, but this is, you can also just use regular Desmos. So when you're doing this, I'm going to do 8 and then type in exclamation point, and it will do that math for you. So it is going to give me 40,320. Now let's change this to a 7, and I get 5,040. Let's change this to a 6, I get 720 and change this to a 5. And for that, we get 120. Okay, and then I'm going to do 4 factorial. And we get 24. I'm going to do 3 factorial. And we get 6. I'm going to do 2 factorial. And we get 2. I'm going to do 1 factorial. And we get 1. Which result is the same number as the number of Marcus's possible schedules? So if we look at his possible schedules, we see that his possible schedules was 720. And we see that that's this one, 6 factorial. Which result is the same as the number of possible schedules? So this one is 6 factorial, which equals 720, is the same. And remember, we did that by taking 6 times 5 times 4 times 3 times 2 times 1. What do you think 6 factorial means? Why does it give the correct solution to the number of ways that you can arrange Marcus's schedule? So 6 factorial, it looks like, is equal to 6 times 5 times 4 times 3 times 2 times 1. And if you take a look up here, 5, you have a 1 here and a 1 here, okay? Ignore this 1 for a second. 5, 4, 3, 2, 1. 120 is the same as 5 factorial, okay? And then for this one here, ignore this 1 and 1 because 1 times 1 isn't going to change anything. 4, 3, 2, 1 was 24, and that was 4 factorial. So that is going to be, so anytime you're doing any number factorial, okay, so if I was doing x factorial, it would be x times the number less than x, which is x minus 1, times x minus 2, dot, 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 times all the way down to timesing it by 1. Okay, that's what we're going to be doing. Explain why 4 factorial gives a correct answer to the possible ways to arrange the letters in the word math. So if we're arranging the letters in the word math, we've got first spot, second spot, third spot, fourth, okay? So we're taking each of these letters, M, A, T, H. And how many letters can I pick from for my first one? Well, I can pick 4. How many can I now pick for my second one? Now that 1 is already picked, because I'm using these. Think of these as having little tiles, like you have an M, an A, a T, and an H, okay? So then there's going to be 3, and then 2, and then 1. And this is 4 factorial, which is 24. So instead of typing out 6 times 5 times 4 times 3 times 2 times 1, or 4 times 3 times 2 times 1, we can use that factorial button. Remember what n factorial means can help you do some messy calculations quickly, as well as help you do problems that might be too large for your calculator's memory. For instance, if you wanted to calculate 9 factorial over 6 factorial, you could use the factorial button on your calculator to calculate it. To calculate 9 factorial and 6 factorial, so you get this. So they're showing us over here on the side, I'm going to do 9 factorial over 6 factorial, and you see we got this. Now, if I wanted to just do 9 factorial, you see that was 362,800, and then 6 factorial, that is 720. And so we can take, I'm just going to copy, see if I can copy this. Let's see if it'll let me. divided by, oops, not minus, divided by 720. And I get that same thing. So here we did 9 factorial over 6 factorial. Here we did 9 factorial, 6 factorial, and then we worked that out. Now they're showing us another way to think about it here. So they wrote out 9 factorial, okay, as 9 times 8 times 7 times 6 times 5 times 4 times 3 times 1, and 6 factorial, 6, 5, 4, 3, 2, 1. And what you'll notice is you'll have some things that will cancel out. So here, I've got a 6, 5, 4, 3, 2, 1, and another 6, 5, 4, 3, 2, 1. They're all going to cancel. 6 with 6, 5 with 5, 4 with 4, 3 with 3, 2 with 2, 1 with 1. And what are we left with? We're left with 9 times 8 times 7. That's what we're left with, which is 504. Okay. So over here, let me show us what that is. So let's just show that if I was to do 9 times 8 times 7, I get that 504. Okay. So what they want us to do on this is they want us to simplify the following without using the factorial function on your calculator. So in this problem here, what you want to do is you want to break down the 9 to 9 times 8 times 7, and we're still going to do 6, 5, 4, 3, 2, 1, but another way to write 6 times 5 times 4 times 3 times 2 times 1 is 6 factorial. And then you'll notice on bottom, we had a 6 factorial. And so what I just wrote here is really the same as what I had highlighted in green over here. 6, 5, 4, 3, 2, 1 is really 6 factorial. 6, 5, 4, 3, 2, 1 is 6 factorial. These are going to cancel out and we get 9 times 8 times 7, which is 504. That's what we want to do on these problems. So on this one, I'm going to take 10 factorial. Just going to move it over here. And I'm going to break 10 times 9 times, and then I am going to do it as 8 factorial over 8 factorial. And then the 8 factorial on top and bottom are going to cancel out. And I end up with 90 as the answer. So on this one, when we have more than, when we have 70 to 68, okay, I'm going to start with 70 times 69 times, and again, I'm going to do 68 factorial over 68 factorial. Those are going to cancel out, and I am going to end up getting 70. Let me clear this. Clear all. I'm going to end up getting 70 times 69, which is 4,830. Now, on the bottom ones, what you want to pay attention to is we have 2 things multiplying on bottom. And what I want you guys to understand is I cannot take 4 times 3 and get 12 factorial, because 4 factorial is 24 times 3 factorial, and that's going to be 144. Now, if I was to take 12 factorial, that is going to be a lot, because what is 12 factorial? Remember, 4 factorial is 4 times 3 times 2 times 1 times 3 factorial is 3 times 2 times 1. I'm not going to, I'll get a 12 here, but I'm not going to get all the rest of this. 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, and 1. So as I'm doing this, again, I'm not going to have an 11. I'm not going to have a 10. Okay. I'm not going to be getting a 7 for sure ever up there. So you cannot multiply these together and get a 12. These are not going to be the same thing. Just want us to understand that. Okay. Now, what I want to do, or what I would recommend doing on this, is I would take the 7 factorial down to the biggest and the 20 factorial down to the biggest. So for this one, I'm going to go 7 times 6 times 5 times 4 factorial over 4 factorial. And then my 3 factorial is going to be at times 3 times 2 times 1. I'm going to write that out. Then I'm going to cancel some things. So let me do it with a highlighter. Okay. So my 4 factorial and 4 factorial would be gone. My 3, 2, 1 is a 6. So that's all gone. And so my final answer is going to be 35. Now on my next one, I'm going to start with 20 times 19 times, and again, I'm going to break it down 18 factorial. Then on bottom, I'm going to have a 18 factorial times 2 times 1. So again, when I simplify this 18 factorial and this 18 factorial are going to be gone. This 2, well, 2 times 1, if you want to think about that, is going to go into this 10. And that's going to go into the 20 10 times. So I'm going to get a 10 times 19, which is 190. And just to verify this, I'm going to show you that 7 factorial over 4 factorial times 3 factorial did give me the 35 here. And 20 factorial divided by 18 factorial times 2 factorial did give me the 190. So hopefully this will help you out on the classwork if you didn't finish it in class.